Okay, I also asked that you consider that if the water goes that far at the beginning, it's probably going to go less and less far because you have less and less pressure as the water gets shallower, okay? And you don't have to have a PhD in physics to understand that conceptually, okay? And in a freshman physics course, you would learn why that happens. But what does that do to your depth versus time graph? Well, let's see, I was thinking the graph looked like this. Is that right? What's wrong with that? I think it's a very pretty graph. And that's the only real criterion for being correct. If it's pretty, it must be right. Is that right? Hey, y'all are laughing at me. That's not nice. Okay. Well, no, it doesn't. What's wrong with that graph?
It's not a function.
It's not a function. Why should it be a function?
Because the amount of time is only going to have one.
Yeah, it comes down to any time is going to occur only once during this, right? And there is one depth at that time, whereas this time it would seem to imply 1, 2, 3 different depths, right? So it's got to be a function, okay? It's not like there's a set of stone tablets that came down and said a function has to have pass the vertical line test. It's that what we mean by a function is, if I tell you the time, you tell me the depth, not 2 depths, not 3 depths. It's a common sense idea, okay? Didn't come down to stone tablet, there's a reason for it. I want you to be able to think about reasons because it makes it easier to remember rules, okay? So anyhow, one rule is, of course, never believe anything that I put on the board after that, okay? You're laughing at me again, don't do that. Okay, now, okay, how about this? We saw that didn't work for a pendulum, right? But in this case, the depth will eventually reach 0. You know that the thing will eventually stop leaking, okay? So there's nothing wrong with having a horizontal intercept to the graph, right? And of course the depth starts at something, and that's okay too, right? Whatever this point would be indicates how deep it is when time is 0, right? So there's nothing wrong with having an intercept here or an intercept here, or having both. So what's wrong with this?
It implies constant pressure.
Again?
It implies constant pressure.
It might imply constant pressure. There's a connection, and the connection is the further the water goes, the faster it has to be moving. And the faster the water's moving out of here, the faster it's leaking out of here, right? So if you accept that the pressure decreases with depth, and that the distance the water stream goes has to reflect how fast the water's coming out, you conclude that it really kind of has to look something like this. Okay? Does that make sense? All right. Well, now here's a x squared graph again. Does this look like it could be part of an x squared graph? Well, yeah, you know. I mean, I have a little different scale here. Time is extended more, and maybe the vertical. But if I take, let's just say this part of the graph and put it on a little different scale, it might look like this, right? Okay? And it turns out that it does. And I won't say it was one of the most astounding revelations of my life, but about, how long ago, 25 years or more ago, I tested this. You know, just a plain old bottle. And I did observations and got accurate timing and plotted 3 points. Actually, I plotted a series of points that showed what the depth was versus time. Okay? Now, at the time, everything, we didn't have Windows, it was DOS, and these points were pixels, which means they were really tiny, okay? And then I did, figured out what the curve ought to be for those points. I did the best fit model and plotted it, and the graph, by darn, went right through every little pixel. And the graph was very thin line, okay? Which showed me that, yeah, I expected it would be close to quadratic because that's what physics was telling me, but there's viscosity and other factors that I figured would throw it off, and they didn't. Not at all that I could detect, okay? Totally impressive. Well, you're going to learn how we can do that model, although I'm not going to teach you how to do a best fit. You go to Excel, it'll do the best fit for you, okay? And we're not going to do that. We're going to do it by simultaneous equations. Now, the way you really do the best fit either involves linear algebra or calculus. There's a way to do it with linear algebra, there's a way to do it with calculus. So, I'm not going to obviously address that in the class, okay? That's something you get about second semester calculus. And it's pretty tough in linear algebra, it's pretty abstract. Okay, so anyhow, my point is that this thing ought to be really well modeled by a function that's based on this curve. The curve ought to have the same shape as the decreasing part of this curve. Okay? That's a big deal. And this function is y equals x squared. This function is like this, okay? Where we replace x by x minus some number. We have an a out here, and we add a k out here, okay? If you have 3 points on this graph, so you know x and y, 3 times in depth, right? Just 3 of them. You can plug the time and depth in, first time in depth, and you get an equation. The next time in depth, you get another equation. The next time in depth, you get a third equation. And you can solve those 3 equations for a, h, and k. It's really not difficult, okay? So we're going to see how to construct that function. We're going to see that that function works for this model. And we're actually going to reduce the 3 equations to 2 and then talk about simultaneous linear equations. When we're talking about time, instead of x, we typically use t, so I'll put a t in here, okay? And here's another way to write the model. Now, what kind of an expression do you call this? At squared plus bt plus c. It's a quadratic function. And how do you, what's something else that starts with the word quadratic that you learned in your algebra courses?
Quadratic equation.
You have quadratic equations. So if I set this equal to something, well, this actually kind of is a quadratic equation too, isn't it? This is equal to this. Okay? So let's see, a quadratic equation in standard form, it looks like this. Actually, I'm probably misusing the word standard, but we won't worry about that. Okay? How would I solve that equation? What do you mean by solve it? It means you find an x that you put into this equation and you get your solution, right? Okay? So how do you solve a quadratic equation? What's another word that follows quadratic? Another F word, not function. And not that other F word, you know, that thing that you need to use distributive law for. Okay? You ever heard of the quadratic formula? Anybody remember the quadratic formula? Not expecting that you would. You know, I went to pretty selective school where there's science and math, okay? And not soft sciences like biology. Hard sciences, things you can touch and beat on. Physics, chemistry, metallurgy, okay? You really don't want to beat on steel, but still, get the idea, okay? And I remember the quadratic formula, and I was in not the top level math class. You pretty much had to be in a East Coast prep school to learn before you got to college. But you know, the next level, we got an actual professor. Okay, so I was in a fairly selective class in a very selective institution. And most of the students in that class didn't know the quadratic formula. I was shocked. Students in my school knew it, and used it. Okay, so if you don't remember, it's okay. But, I'm telling you now, starting when you walk in here next time, you need to know it. Okay?
Thank you.
Simple enough, you recognize it, I hope. I'll probably write that into your homework and ask you just to do a couple simple examples, just so you get your hands on it, which makes it easy to remember if you use it a couple of times, but nothing overly difficult. Okay, you got to know that. And we'll talk next time about how you recognize a quadratic equation when it isn't in this form. It's real important to do that. Okay. Okay, let me stop for just a minute. Take a look at something so I know what to tell you next.